Hello everyone, my name is Wesley Rollins. I'm a senior in ocean engineering at the University of Southern Mississippi, and my senior project was optimizing thrust of a biomechanical fish. The motivation was, unlike traditional propeller-driven systems, bio-inspired propulsion can reduce noise, improve efficiency at smaller scales, and better replicate natural aquatic locomotion. This is useful for observing fish naturally without disturbing them. The OpenFish project demonstrated realistic thuniform swimming behavior, making it an ideal baseline platform for evaluating thrust generation and tail performance. This video demonstrates the original OpenFish swimming behavior and highlights the realistic body and tail motion that inspired this project. And this is a clip of the paper on the left side of the screen. The problem was, how do we accurately measure small and steady thrust forces produced by a flexible robotic tail fishtail? The primary challenge was separating very small thrust forces from noise, vibration, and mechanical interference while keeping the system simple and repeatable, as well as low cost, and allowing modular testing of multiple tail configurations and RPM conditions. The objective and the overall goal was to develop a low-cost experimental platform by designing a thrust measurement test stand capable of quantitatively evaluating robotic fish propulsion performance and calibrating both systems to work in harmony with each other, then using them to run extensive testing on caudal fin configurations and RPM conditions, analyzing this data to see which performed best and created the most thrust. Those two systems were the thrust measurement rig, which was designed to keep the fish stationary while measuring force output, and went through multiple design iterations to improve simplicity and accuracy, as well as the robotic fish, the propulsion device used to generate the thrust, tested under different RPMs and different caudal fin configurations. The integration of these two systems allowed controlled propulsion testing while directly measuring generated thrust forces. For the rig iterations, the first one on the far left here is a sliding cart pushing against two compressive load cells. It would have a lot of moving parts and complexities. The second one in the center was the first vertical hanging configuration, which allowed easier access to the fish and a smaller tank. But the tail proximity to the bottom would have created undesirable wave reflections and interference. Iteration 3 was a horizontal rig using a pivot bearing and a tensile load cell. This would function successfully, but introduced more unnecessary moving components. These early iterations helped identify major potential sources of measurement error, including unwanted moments, alignment issues, and mechanical complexities. Iteration 4 is a simplified version of Iteration 3. It still relied on a rotational bearing and introduced a slight directional tilt. 5 was designed to keep the top section accessible for rapid internal modifications, but created complications of the fish weight distribution and calibrations, as well as hanging angle effects on the load cell. 6 was the closest design to the final rig configuration. It used a moment arm connected to the load cell to convert bending into measurable force. Through iterative CAD designs, the design evolved towards minimizing moving parts and reducing off-axis loading effects. For the final rig design, we used a simple wooden beam mounted across the top of the tank, and the fish was held stationary beneath the beam using a flat steel moment arm which connected the fish to the load cell. The load cell and the fish were both mounted using L brackets. The main advantage of this was significantly simpler and more repeatable system, as well as cheaper. The main challenge with committing to this iteration was that the fish required complete waterproof sealing due to its full submersion. The final rig provided the best balance between simplicity, rigidity, accessibility, and measurement consistency. The laser pointer. As you can see in the photo, the load cell is on the top between the beam and the water, and the fish's caudal fin is fully submerged to have the least disturbance to the surface. The fish is also moved forward to not create unwanted reflections from the rear of the tank. The cables run from the power system up into the speed controller and then down into the head of the fish to control the fish's RPM. The ESP32 communicated through a cable here to a laptop off screen. This final configuration successfully reduced unnecessary mechanical interference while maintaining accurate force transmissions to the load cell. The other system is the fish, the robotic fish platform. Based on the open source OpenFish design, modified for testing compatibility, and a combination of 3D printed parts plus some off-the-shelf components. The bottom left figure shows the expanded CAD figure of the whole assembly. The right image shows it put together with the removable top section exposing the internal components and the motor assembly. Using an existing validated robotic fish platform allowed more project effort to be focused on experimental testing and propulsion analysis. For the propulsion system, it was a motor-driven gear system with cable-driven tail actuation that produced lateral oscillations. The figure shows the original CAD and the updated design in the photo here to show the differences that were made. The motor outputted into the shaft coupling, and then into a 90-degree gearbox with a 20-tooth gear at the top of that drove the two 50-tooth gears on each side here at the top photo. With this, it pulled the cables that you can kind of see here in orange down the length of the tail, creating tail oscillations that generated forward thrust. This cable-driven system allowed compact internal packaging while producing realistic fish-like tail motion. The top shows the CAD fish cutout across the midline from above. The gear system in the center is turned on the bottom for the bottom CAD assembly here. So the pink is here and here as well. And then the real-life CAD or assembly here in the center. Next to it shows the two 50-tooth gears and the 20-tooth gear in the center and how they output to the shaft collars. They were mounted in opposite direction to produce that left-right movement needed. This mechanism converted the continuous motor rotation into controlled lateral tail motion. And the zoom into the CAD here shows the collared bolt that free spins within the oil-impregnated bearing, creating or not allowing the cables to be tangled on each other and the motor itself. The cable motion transfers oscillatory movement from the active section of the tail into the passive section of the tail, which produces thrust. The active section is here with the spinal column looking things, and the blank section is the passive section here, which led to the caudal fin on the end of that. The passive tail flexibility is critical for generating forward thrust. The water is redirected backwards at an angle to propel the fish forward, and the proper deflection produces realistic thuniform swimming motion. Thuniform locomotion is the minimization of head motion while maximizing tail-driven propulsion. While my fish is not free swimming, having the least head movement while attached was optimal for this study. The tail must balance the flexibility for bending and the stiffness for force transfer. The observed semi-S shape here in the body curvature closely resembles biological fish swimming patterns and indicates effective moment transfer into the surrounding water. These vortexes shedding off from the back is what forward thrust looks like from a real fish, and this can be achieved with the proper active tail and passive tail segments, as well as the correct drag on the caudal fin. The tail flexibility is critical for this realistic propulsion, as well as waterproofing the rear of the fish, creating a seal. A silicone casting process that used molds and clamp compression during a 24-hour curing process was done. Some of the issues encountered were weak points along this line here, and the initial design experienced tearing near this high deflection region. The solution was to bevel the leading edge, which increased the silicone thickness in the high stress areas for version 2. As you can see, the CAD figures are not the same size. That's because the top was increased by 10 millimeters to allow the surface area increase the surface area being sealed to the body of the fish. This would prevent pulls and rips from happening. The iterative fabrication improved the structural durability and the seal on the fish. Photo 1 shows additional silicone being applied to reinforce the weak point on the silicone tail version 1. And through experimentation and efforts to seal the tail onto the fish, I discovered liquid electrical tape, initially used for waterproofing, the black here in the second photo, did not adhere to the silicone tail, but did fill the gaps in the fish's body, as well as Flex Seal being used to seal the main body, the midline, and the wire entry locations, as well as the L bracket holes on the main body. The final successful seal between the silicone tail and the PETG body was achieved using an RTV gasket maker. Reliable waterproofing was essential because any leakage could damage electronics and invalidate long thrust testing. After this, testing the fish in fully submerged water to see if it leaked or not. Observing for escaping air bubbles, which would indicate leaks. The successful test confirmed waterproofing integrity before thrust experiments. And on the right is a photo of the drying process for the Flex Seal on the main body of the fish. This verification step ensured the propulsion system could safely operate underwater during these testing sessions. For the thrust measurement system, as the fish swims across the direction or through the direction of the arrow against the load cell, creating a bending moment in this section with a hole here, the Wheatstone bridge crosses the section, which is this, and the bending moment happens in elongating or compressing these resistors. This creates a change in voltage across the Wheatstone bridge, which is proportional to the force being applied. This is an output in analog, and then goes to the HX711, which amplifies and converts the data into digital, and it goes to the ESP32, which then runs the uploaded code of conversions and transfers the data to the serial plotter. From the serial plotter, we watch live data being collected and is recorded and then exported into MATLAB. From MATLAB, we process the raw force time data, then I use it to generate the plot's performance comparisons between testing sessions. These measurement systems enabled continuous real-time thrust analysis during the swimming experiments. Early hand calculations estimated a maximum thrust near about 3.5 newtons. This is with 100% motor efficiency, which was equivalent to about 1.2 kilograms. So I chose a 1 kilogram load cell, which would fit the appropriate expected thrust range and better sensitivity and resolution at the lower forces, where the test would be done. It was also a cost-effective solution within the project budget. Preliminary calculations helped guide sensor selections and ensured the load cell operated within an optimal measurement range. Without the calibration, this data is meaningless. So I took the open source program that gave an output of grams from the load cell and added in the conversion to force, as well as adding in time steps to accurately show the force over time and be able to conduct swimming tests for equal lengths per test. The graph on the bottom right shows an example of a force over time for a quick hand pressure test on the load cell to prove the code outputted in the desired manner. The testing procedure was mounting the fish, turning everything on, recording a short baseline, and then running at a fixed RPM for 2 minutes. Recording this thrust data, then exporting it to MATLAB, where it was analyzed. Keeping the test duration and operating conditions consistent improved repeatability across trials. The video is the first successful run that the fish completed. He was then named Giovanni afterwards. This graph is a raw thrust signal plotted over time and connected to show the oscillatory force behavior. The green line is the positive average thrust, and the red line the negative average thrust lines included for comparison. The periodic thrust pattern confirms successful transfer of oscillatory tail motion into measurable hydrodynamic force generation. And as I'll show you in the next slide, this particular graph is highlighting an inefficiency in force propulsion. The caudal fin 1, pictured in the top right, the CAD version, test was done at 450 RPMs, producing strong forward strokes about 1.2 newtons, but it also spends significant time in recovery and backflow motion. The close proximity between the positive average and the negative average thrust values suggests this tail configuration was not highly efficient at producing sustained forward propulsion. This shows that the first fin tested with is not producing much forward thrust, and to see the differences, I designed more caudal fins. These are the 2 different caudal fins. The skinnier one on the left in both of these is the first one, and the larger one on the right is the second one designed. Unfortunately, due to load cell failure, full quantitative comparison between all fins and RPM conditions could not be completed. However, qualitative flow visualization and tail motion observations still provided valuable insight into propulsion behavior. The direction of the water is pushed is just as important as the amount of tail movement. The initial fin design primarily pushed water side to side, and the larger fin generated greater drag on the passive tail section, creating an angle of attack that was more appropriate, and this increased the forward thrust movement. The larger caudal fin produced more realistic tail motion and redirected flow further behind the fish rather than primarily left and right. The CAD models show the progression, and then even without the complete thrust data sets, the visual changes in flow direction and body curvature strongly suggested an improved propulsion performance with the larger fin. The screenshots on the bottom left are from the 2 videos, left being the original fin for the video and the screenshot. As you see in the screenshot, the dye is dispersed left and right, and in the screenshot on the bottom right, the dye is dispersed in vortexes. This was the dye injection method used to observe the wake flow formation. The original fin configuration, dye primarily dispersed left and right, indicates energy loss to lateral flow rather than forward propulsion. And in the right video, the larger caudal fin configuration increases rear tail deflection, and the dye is pushed further downstream behind the fish. The flow visualization clearly demonstrates how tail geometry changes altered wake direction and likely improved the thrust efficiency. The larger fin produced a more concentrated downstream wake, indicating better moment transfer and desired thrust direction. As far as system validation and repeatability, although the data set was limited, the system successfully validated the ability to measure small oscillatory thrust forces from a flexible robotic fish platform, showing a repeated peaks, oscillatory frequency, a stable baseline noise in each of the iterations completed until a certain point. For my budget, it was provided through the Ocean Engineering Laboratory. Thank you, Dr. Nunes. No outside or DCRA funding was obtained for this project, and the budget constraints influenced material selection and testing scope. Despite this limited funding, the project successfully produced a functional experimental propulsion testing platform at a relatively low cost. The limitations, the load cell failure limited the quantity of thrust data collected. Only 1 tail configuration was fully quantified, and limited RPM testing was completed. Waterproof sealing process still requires some improvement, but some of the additional observations still gathered were the dye visualization, tail deflection analysis, and wake direction behavior. Although the numerical data set was limited, qualitative testing still provided important insight into propulsion performance and tail behavior. as far as what can be improved, the deflection of the caudal fin to achieve thrust in the X direction, reducing noise and vibration noise in the measurements, and improving the alignment of the load path. Using a higher precision load cell, or one that doesn't break, and better waterproofing for future aquatic testing, as well as using some rust-resistant materials for the testing rig. Future iterations should focus on improving both hydrodynamic efficiency and measurement precision simultaneously. Reducing mechanical noise and off-axis loading would likely improve the consistency of collected data. For technical skills learned, I work directly with load cells and calibrating programs, integrating with an ESP32 microcontroller and an HX711 amplifier for real-time data acquisition. I repeatedly redesigned components in Fusion based on testing feedback, using a serial plotter for raw data collection and MATLAB used to process, smooth, and compare thrust data. This project combined mechanical, electrical, and software engineering into a single experimental testing platform. For soft skills learned, and seeing as we presented every week for at least 30 minutes, some of us for longer, I learned the importance of communicating technical systems clearly, both visually and verbally, especially when explaining complex mechanisms like the propulsion and thrust measurement system. This project reinforced how engineering research is often iterative, where each version builds off of previous work and gradually improves through testing and redesign. This project required balancing technical development, testing deadlines, fabrication challenges, and data analysis simultaneously. One of the biggest lessons learned during this project was adapting to unexpected hardware problems while staying on schedule. A large amount of the project involved troubleshooting systems that I had not tested together before. And simplifying mechanical systems often improves their measurement quantity more than adding complexity to them. This project also highlighted how experimental engineering rarely progresses perfectly linearly, and redesign is a normal part of development. For future work, testing additional fin geometries and surface textures, comparing hydrophobic and hydrophilic laser engraved tails, expanding the RPM testing range, and investigating biomimetic surface features such as whale tubercles. The laser engraving and surface modifications were considered during the initial planning, but time constraints prevented full implementation during this phase of the project. The completed platform now provides a reusable foundation for future propulsion and hydrodynamic studies. Future testing could combine a quantitative thrust measurement with flow visualization to better correlate wake structures and propulsion efficiency. In conclusion, the project successfully integrated mechanical design, embedded systems, fabrication, experimental testing into a functional bio-inspired propulsion research platform. This work provided a solid foundation for future robotic fish propulsion studies and improved hydrodynamic optimization, as long as you replace the load cell. Some of the acknowledgements was Dr. Newts for feedback and some funding privately, Bryce Hogan for some donations, and Noah for some 3D printing expertise. Thanks, man. Questions? You first.
Okay.
No, I don't think so.
So the first question is that it seems that your fish just like moves so fast with tail. So then I was asking this question from myself that how fast a fish really moves its tail while it's swimming. That's probably why you were getting a lot of like lateral, like you're literally doing a fishtailing rather than.
Yes. So in the, I meant to grab the other, but you saw the comparison of the two caudal fins. At that same RPM, so both those videos were the same RPM. It was 450, and you can tell the left one is doing a lot of lateral movement, and it's at that RPM. But this larger tail was at the same one, and it moves a little bit slower. It's the higher drag on this. I tested at other RPMs as well, but those are the most visually stunning for a video. But at 450 RPMs, this operates at about 2.4 hertz for both tails.
I would say that in reality, a fish tail follow like sinusoidal range.
Mm-hmm.
You should have tried to do that.
Yes, that was the inherent hope and goal, but having this passive tail section bend is the closest I was getting to the sinusoidal direction, so having it look like that was what the goal was. This wasn't quite achieved.
And then you showed us the thrust, and you said that it's not very efficient. If you go to the graph,
The bar graph?
yeah, no, next one.
No.
So,
No. Okay.
how does an efficient one look like?
Unfortunately, the load cell broke, so I don't have data from this one to show you that. I only meant inefficient, as in highlighting how close the positive thrust versus the setback was, and just stating that they're too close for there to be much forward thrust. And that's because of the more lateral movement, as opposed to actually getting that angle of attack and pushing the fish forward. But I did not get to get a bar graph or another data set from that, unfortunately.
Then again, you were missing that FFT analysis to show what is the frequency that contains the oscillatory flux.
Yes, sir.
I guess future work also should be get it first done with making some efficient process, and then go into reusable.
Okay. Thank you. No?
So Leslie, yeah, sorry, Leslie insisted. So my question is,
I don't know if I did, but those are your words.
and have you looked into, since you couldn't measure the thrust for the second tail option, have you looked into the literature on whether you can back calculate the thrust based on your dye experiments and the size of the vortex that the tail is shaped?
Not recently. In the first semester, what? In the first semester, I looked into doing analysis with, I'm forgetting the term, but there's lasers, and you watch the vortex shedding, and you calculate thrust that way. But those lasers and stuff along that way were very expensive. But maybe, yeah, I think so. But not recently, to be able to answer the question now. And also the load cell broke a week and a half ago, so I was behind, entirely my fault. And so when that happened, it was a bad time.
No.
Yep.
Sorry.
So, for your first tail, you said it seemed like it was having more thrust in the side-to-side motions as opposed to the forward-backward motions, which is what you would want. How would you kind of pose measuring to the side-to-side and the forward-backward, either individually or at the same time, to be able to compare and be like, this tail produces the most forward thrust as opposed to side-to-side thrust?
Oh, I would recommend not breaking your load cell.
Oh, yeah.
And quantitating it that way, following through and testing each caudal fin at the 3 sets of RPMs to see which one produces the most thrust. As far as without the load cell, doing vortex shedding math would work, provided time, of course.
Do you think it would be possible to like fully eliminate any of the side-to-side thrust, or is there always going to be some amount of side-to-side thrust there, and you can only try and mitigate it?
Specifically with Giovanni, there will always be some side-to-side thrust because it's not creating that S, that sinusoidal, as efficiently as a real fish would. Creating a different fish, you may be able to eliminate that or produce that S and then be able to eliminate the side-to-side as much as possible. But inherently, flapping left and right will create left and right thrust. It's just getting that angle of attack as you push to be able to achieve the forward thrust over the left and right thrust.
And that's because the tail is hard on its own, right?
What?
The tail's in the very last.
The passive tail section is flexible, yes.
You want the actual hard part though is inflexible.
Correct, okay, yes,
And that
I understand, yeah.
prevents that shape as well.
Yes. There's a lot of fish with a lot of different designs. Some of them have massive, very flexible ones, some are very stiff. So there's a lot of different ways you could test it, a lot of different caudal fins you could test. I did actually, unfortunately, forget to mention, this was a third caudal fin that I designed, but did not end up 3D printing or testing. Close to. And it had the same surface area as tail 1, but different shape.
That would
I was interested, unfortunately. Yes, Joseph.
What do you think was the actual issue with the load cell? Like, was it just a cheap load cell, or what do you think actually did it?
So earlier in the early in the second semester, it stopped working entirely, and then it just came back for, as far as I can tell, no particular reason. And then potentially that's what's happening here. Maybe it just needs a little rest period, but I don't know. Potentially I got water in the breadboard and fried it, but the HX711 and the ESP32 continue to work, but the load cell did not. And the sections that I'm compressing here don't contain the Wheatstone bridge, which is how you get that data. So I don't think that I compressed it too much to break it that way.
Would you recommend people buying a different load cell, or do you think it's just something serious?
I think this is a great starter load cell, but you should plan to have probably a better one whenever you go. Also, this was a quite cheap one from AliExpress. There's there's a decent amount of noise from it, and getting a more expensive one that reduced the noise as well as increased the accuracy would be more efficient anyway. I'm not standing in front of the camera. Yes, Matt.
This is more just like real life. Have you taken into account the fish aren't really that smart? So like, let's just say like you got a Goliath grouper near you, whatever. You're by like an oil rig, or you're by a boating dock, and this grouper inhales it. How to adjust that possibility? Oh, having that one.
Of this one getting eaten?
Yeah, like fish or dogs.
That's $212 I don't have anymore. That's about it. That's about all I got.
Okay.
Yeah, in the original propulsion when I was in what's the class? 389 was a much larger grouper style one, so that it wouldn't be hunted by other fish.
Yeah.
And I think
that can always be scaled too.
Yeah, and if I scaled it, it would be the Reynolds number. Thank you. But originally it was going to be much larger, and I think my budget for that was like $40K. That was before I understood what we were doing here.
The cell was paints you can put on your fingernails to make them bitter, so you stop biting your fingernails.
Yeah, that's true. I could make it acidic, or just pufferfish needles. Something crazy.
Lionfish.
Yeah, lionfish.
Lionfish. Okay. Yeah, that's fine.
Okay. But yeah, the original design was actually a grouper. I don't fish, and I was advised actually by them to not make it a grouper.
Originally, you wanted to look at like small creatures, and if you're trying to observe small creatures, don't make them look like it.
Yeah, the predator. I did not know that, but thank you for teaching me, John. Any further questions?
So you were talking quite a bit about how important it is to adjust the flexibility of your tail. Is it just the flexibility, or is there's a combination of the flexibility and something else needs to be adjusted?
It would be a combination of a couple different factors. One of them is the flexibility. A second step of the flexibility combination is this silicone section of it is quite thick, and in my original.
So that is just the flexibility.
Yeah, but it's not just the piece of plastic that's under here is quite flexible, but this section also reduces the flexibility. As well as the drag on the caudal fin, and then the force produced. There's a lot of those factors mainly.
So do you think you need to change the flexibility if you change the fin?
Potentially, but optimizing the fin for the current flexibility is also a choice. No, my answer is no.
Yeah. Well, I think you do, because the bigger fin needs the stiffer tail, so that the angle of attack is the right way.
I think you're correct. I think this flexibility with this tail worked quite well together, at least visually. And if I increased the size of it, I should stiffen it. You're correct. And if I decreased it, I should loosen it, which is what I saw with the original fin having that left to right movement. It wasn't creating enough drag to create deflection on the tail, passive section of the tail.
So what could you do to that you change the flexibility? Parameter that you change?
One could be just increasing the thickness of the spinal piece that's in here, just so it takes more force to create a bending moment.
You also change the actual silicone.
Yeah, I could also change the material of it to a stiffer material.
Because I think the silicone is the most influential factor there. internal structure is probably pretty neglectable. My guess.
Yeah, I mean,
Places that do not.
I don't know how neglectable it is. Most of this comes from the interior, but I would say that the silicone is more of a binding factor, yes, sir. And the one that broke didn't work too well. But that's the
lower
cutout.
part, which is solid silicone. It also
Yeah.
has the flexibility, no?
Really?
No, you did the top part.
Yeah, this is just a 100% infill basically of silicone.
Right,
Yeah,
it
it
makes
is.
it pretty stiff.
Yeah. And yeah, I can decrease the thickness of it to increase the flexibility, yes, sir, for that section. Yeah.
Did you think about like adding pectoral fins, or I see you said you had a third, yeah.
Caudal fin, yeah.
Did you have like any other ideas for like a Thrasher shark maybe?
Originally I had I think 5 different options, but the goal was to create one fin that worked the best, and then the original goal was to create one fin that worked the best, and then try hydrophobic and hydrophilic laser engraving, see which one of those produced the most thrust. So I wasn't too focused on the fin shape itself. That's what I wanted. I didn't get to it, obviously, but that's what I wanted to do.
Yeah, I just know Thrasher sharks they got that long.
Is that the one where it's shorter and it's way longer up top?
Super long,
Yeah.
yeah.
I would be limited by tank space,
Yeah.
but that would be really cool to see.
I didn't know if it could probably help with like your thrust overall because they are like a fast shark.
The original design that I had was a tuna's fin.
Okay.
That's not what this is, but
Yeah,
the
that's similar, but
Yeah.
I know what you're saying.
Charles, you had a question? Oh, what'd you raise your hand for?
Marlin fin.
Something. Okay.
This was just saying.
Don't forget to like and subscribe.